In order to better understand an electric field and what it is, we need to first understand how to represent them visually. If we understand how to draw them and how to interpret these field diagrams if we're given them, you'll find that it's much easier to analyze the changes in energy or the changes in potential or voltage or all these other terms that we're going to discuss as we move forward. So in this video, I'm going to try and explain to you how to draw these electric fields, how to analyze them, to at least give you a starting point as to visually representing them, which makes it easier to kind of physically analyze them. So to start with, I'm going to make a connection to gravity because I think more people have an innate understanding of gravity just from their daily experiences in life. And because it's a field, just like electricity is a field, there's a lot of similarities. So we can use gravity to try and better understand electric fields. So let's imagine we have a room. This is kind of the side view of a classroom with the floor on the bottom and the ceiling on the top. If I place a mass at this location in the room, I think we all understand that the force of gravity is going to pull that mass down. If I let go of it, it's going to start to accelerate downwards. If I placed another mass at this location, same thing. If I placed a mass at a third location, same thing. So no matter where I place a mass in this room, it's always going to be pulled downwards with the force of gravity. So what we can do is to represent the gravitational field that's in this room is we can really just draw a bunch of arrows that are pointing downward. Those arrows tell me that anywhere in this room that I place a mass, the force of gravity will be pulling downwards on that object. And the reason it's called a field is because the Earth doesn't need to touch that object in order to exert that force. Just being in the space around a mass, such as the Earth, is enough for gravity to act on you. So any time that's the case, where this contact isn't required, we call it a field force, and we can represent it with what we call field lines. So those red arrows that I drew, those are called field lines. And in one word, we need to understand that they represent force. So gravitational field lines represent the gravitational force at those locations. If it was an electric field, then the arrows would represent electric force. If it was a magnetic field, I think you realize they would represent the magnetic force. But those arrows represent forces. And the nice thing about them is that the number of those arrows and the spacing between those arrows gives us a lot of information about the strength of those fields, whether it's a strong or a weak field. Case in point, if we had two different rooms, obviously located on, let's say, two different planets, you can tell from looking at these two rooms that it's a weaker gravitational field, or any field for that matter, on the left, and a stronger field on the right. Both because you have more arrows on the right, but the spacing between those arrows is also much closer. So not only does the number tell you how strong the field is, but the spacing between them tells you how strong it is. So if you look at both of these classrooms, the spacing within any one room is the same. So that weaker field has generally the same spacing between field lines. The stronger field, while it's more narrow, the spacing between each line is the same. For that reason, we call these uniform fields. No matter where you place a mass in the room, it's going to experience the same force. If I hold it near the ceiling versus near the ground, it's not going to change how much that object weighs. So the spacing tells us about how strong or weak the field is, but it also tells us whether it's a uniform field, meaning the same everywhere, or a non-uniform field. And just to show you what I mean by non-uniform field, sticking with gravity, if we have the Earth, and same thing, I hold a mass above it, well, that mass is going to get pulled down towards the center. If I hold it on the side, we know from Newton's universal law of gravitation, that is also going to get pulled towards the center. In this case, it's obviously not straight downwards, but then again, what is down, if you really think about it, relative to what? There really is no down. If I place a third mass over here, I think you're starting to see no matter where I place these masses, they're going to be attracted gravitationally to the center of the Earth. So if I want to represent the gravitational field, not in a classroom, but around the Earth itself, it should be a bunch of lines that are pointing towards the center of the Earth. And that's, if you think about it, why no matter where you are around Earth, you get pulled towards the center. That gravitational field points downward towards the center, no matter where you are. But if we look at the spacing of these field lines, you'll notice that the closer you are to Earth, the closer those lines, but the further out you go, the wider they get from one another. That represents this idea that as you get further from Earth, like you've seen on astronauts or spacecraft, gravity gets weaker. As you get closer to Earth, gravity gets stronger. So it's a visual way to represent kind of that idea. All right, so in general, the rules for drawing field lines, and this is really important that you get these written down. They can never cross. Field lines can never cross because that would imply, since those field lines represent force, that would imply that at that intersection point, a single particle would experience two different forces in two different directions, which doesn't make any sense. At any one point in space, gravity is only going to pull you in one direction. So if you cross those lines, you're basically suggesting that there's this weird point where a force can feel two different forces in two different directions, and it's just not physically possible. The second, as I kind of stated before, is that the number of field lines that you use should represent the magnitude or, of the mass or the charge or the magnetic strength, whatever object you're looking at. So what we're saying is larger masses and charges should have more field lines. If you look at a circle that has like 4 lines and you look at one that has 100 lines, you should be able to visually and immediately say, well, one of these is a much stronger field or a much larger mass or a much larger charge than the other. It's all about visually representing these fields. And in the third case, the field line should generally be evenly spaced around the circumference of the mass or the charge. And I just kind of showed you a little diagram on the bottom. You want to be as careful as possible to just make sure that those arrows are evenly spread around. The diagram on the right, where I just kind of place them sporadically, that messes up your spacing. So in the diagram on the right, you're saying that in some sections, like the field spacing is really tight, so it's a really strong field, but then in other sections, it's like really wide, so it just randomly gets weak, and that's not really how these fields work. So we want to make sure that we try and represent the diagrams on the left as best we can, where you show like there's some, I don't want to use the word uniform, but the spacing is kind of even around the outside of the object, and you can just tell that it kind of represents a more realistic field.